Hello, everyone. Thank you so much for joining today. Uh, I'm Vandana, and let's start with the webinar. Yeah. For those of you who are new here, I'll tell you a little about us. Sierra Circuits is a one-stop solution for PCB fabrication, assembly, and component management services. We have a 70,000 square feet PCB manufacturing and assembly campus in Sunnyvale, California. We also offer advanced technologies like HDI, rigid flex PCBs, RF, and microwave PCBs. So this is the agenda for today, and we'll be going into all of these one by one. To understand the significance of RF PCB design, it's important to see, where the market is headed. So here is a brief overview of the RF PCB market size. Uh, So the global RF and microwave PCB market was valued at 1.588 billion US dollars in 2024, and it is expected to reach 2.23 billion US dollars in 2029. It is forecasted to grow at a CAGR of 7.02% from 2024 to 2029. So now let's get to the core topic. So we'll be discussing the four factors for selecting antennas for RF PCBs first. The first factor is the antenna gain. So antenna gain measures how well the antenna directs RF energy in a specific direction compared to an isotropic radiator. It's expressed in decibels relative to isotropic radiation. Higher gain antennas focus energy in a specific direction, hence increasing the range, but it reduces the coverage in other areas. And lower gain antennas offer a wider radiation pattern, and hence they make them suitable for omnidirectional applications. Let's move on to antenna bandwidth. Bandwidth is the range of frequencies over which an antenna can operate efficiently without significant signal loss, and it's measured in megahertz or gigahertz. The bandwidth is determined by the lower and the upper frequencies at which the VSWR meets the 2:1 limit. The antenna must cover the entire frequency band of your application. For example, 2.4 gigahertz for Wi-Fi or Bluetooth, and 868 915 megahertz for LoRa. Also, wideband antennas like log periodic or UWB antennas support multiple frequencies, but may be larger in size. So even with the right gain and bandwidth, your antenna's performance depends on how sensitive the receiver is to incoming signals. So the receiver's sensitivity refers to the minimum signal power level that the receiver can detect, and it's measured in decibel milliwatt. If the receiver has a high sensitivity, then it can operate with a weaker signal, but you must match the antenna to the receiver's sensitivity to ensure reliability with minimal power consumption. If the antenna doesn't deliver enough signal strength to meet the receiver's sensitivity, then the link might drop. For instance, the Bluetooth low energy receivers typically have a sensitivity of around minus 90 decibel milliwatt to minus 10 decibel milliwatt. So size plays a crucial role in antenna design, especially when working with space constraints, in compact devices. The physical dimensions of an antenna are based on its operating frequency and design type, such as the monopole, dipole, or patch antennas. So if you ask why does it matter, then the higher frequencies require smaller antennas, while the lower frequencies require larger antennas. For example, 2.4 gigahertz Wi-Fi antennas are smaller than 900 megahertz LoRa antennas. You can incorporate PCB traces or chip antennas for wearable devices and smartphones due to their compact size. So here you can see a quick comparison among various antennas based on different aspects and their applications here. We have the patch antenna type, dipole, monopole, inverted F, and the chip over here. And the size, gain, bandwidth, and radiation patterns are also shown. So now let's discuss the best design strategies to ensure optimal integration of antennas into RF PCBs. One of the most important decisions in RF PCB design is the material selection. The right materials can significantly enhance the performance while minimizing the losses. Uh, so there are a few tips over here that you can, follow. You can use materials with a dielectric constant less than 4. Examples of these materials are FR 408HR, I speed and tachyon 100G. You can also choose materials with a dissipation factor less than 0.005, like the RO4350B, ITERA MT40, and Megatron 6R 5775. For hybrid stackups, select materials with similar CTs to avoid reliability issues. You can use low profile copper such as VLP and HVLP to minimize conductor and insertion losses. Also choose substrates with high volume resistivity greater than 10 to the power 7 ohm centimeter to minimize leakage currents and energy loss, at high frequencies. Yeah. So moving on, achieving controlled impedance is essential for signal integrity. So here we have 7 guidelines over here to help you maintain impedance control in your design. To remember to keep RF traces short and direct to minimize signal loss and impedance variations. You can maintain a consistent trace width along the transmission line to prevent impedance mismatches. Incorporate a pi network at the receiver end to match the impedance between the load and the antenna. You can match the trace length between the antenna and the matching network as specified in the datasheet. Also avoid stubs or branching in the RF trees because they introduce reactive impedance and disrupt impedance mismatching and impedance matching. Minimize vias in the RF path as vias might cause impedance discontinuities and make sure to use a VNA to measure the impedance at both the antenna input and the output ends. So now we have a small demo on our impedance calculator. I'll just share the calculator here. So our impedance calculator uses the 2D numerical solution of Maxwell's equations for PCB transmission lines and renders fairly accurate results. The impedance tool supports 82 impedance models with multiple geometries such as the uncoated, coated, and embedded microstrip here and the strip line. And with each of this specific model, you can choose single differential pair, coplanars, single-ended, etc. You can see all of these calculators here, and I've just opened a few of these calculators here to just show you, just give you the gist of these calculators. Let's take one of these calculators here for the demo, and I'll enter the dielectric information. Let's go with 3.348 mils for dielectric height H1, a dielectric constant of 3.63. We can enter coating height maybe of 1.5 mils. Coating height H2C and ER2 over here, they already have a default value, but you can change if you want to change them. So let's enter delta W here. Delta W is nothing but the difference between the top of the trace and the bottom of the trace. You can click on this help button, to display a table that suggests delta W values based on the starting copper weight. So I'll just go with 0.5 for now. Enter trace thickness and a trace separation. To calculate the trace width, we need to enter the target differential impedance here and click on calculate W. You can also do reverse calculation wherein you enter the trace width and click on calculate ZD to calculate the differential impedance. And the other parameters here like the coupling coefficient, odd even mode impedance, propagation delay and all will be calculated and displayed. Next, we have the signal loss calculator for the same chosen model. You just enter the dissipation factor here. Go with the frequency, surface roughness. Let's go with 6 because that is a standard roughness for a foil. And let's go with 2 inches for length. Click on calculate loss, and the signal loss output in the odd and even mode are calculated and displayed. Next, we have the S parameter calculator. We enter the source impedance, a load impedance. Use this drop down, to select the output type and click on calculate S parameter. And the uh, S parameter matrices will be calculated and displayed along with the characteristic impedance and the propagation constant. So before using S parameter, make sure that you use a signal loss calculator because the frequency that we have entered in the previous calculator will be used for the calculations here. You can always go back to the signal loss calculator and change the frequencies, if you wish to calculate the S parameters for different frequencies. Then we have the crosstalk calculator here. Let's enter coupled trace length, a signal rise time. Click on calculate crosstalk, and the near end and the far end crosstalk will be calculated and displayed. I'll go back to the slides now. Yeah. So well-designed ground plane minimizes noise, reduces EMI, and ensures signal stability. So let's go over some best practices here that we have listed. You can place RF signals adjacent to ground planes, ideally 1 dielectric away, and do not split the ground planes. Also maintain sufficient clearance between the antenna and the ground plane as specified in the data sheet. You should also incorporate multiple ground vias with lambda by 10 to lambda by 20 spacing around the RF traces and antenna feed. Ground stitching vias will provide a low impedance return path. Use top and bottom ground pose in RF or high speed layouts to mitigate EMI and crosstalk. And the spacing between a high speed trace and ground port should be 1.5 to 2 times the trace width. Also ensure ground ports do not create isolated ground islands because these ground islands can act as unintended antennas. So in addition to electrical considerations, thermal management is also vital in RF designs because excessive heat can degrade the performance. So we have some strategies here to keep things cool. So keep the antenna away from the heat generating components to prevent detuning. And for higher power RF amplifiers, attach heat sinks to dissipate excess heat. Also apply thermal interface materials between hotspots and the heat sinks. Uh, Make sure to, ensure that there is adequate airflow around heat sinks to enhance cooling efficiency. And implement thermal vias with 12 mil diameter and a via to via spacing of 31 mil diameter at least beneath power amplifiers, LNAs and RF transceivers. We again have a small demo on via thermal resistance calculator tool here. So just share the screen. So this is a via thermal resistance calculator tool. It helps you to calculate the number of thermal vias when you enter the drill diameter and the via to via spacing, and also calculates the thermal resistance of single via and the thermal resistance for total number of vias. You can also choose, the via pattern between via pattern 1 and via pattern 2 here. And of course, you have the option to, choose a unit that you're comfortable with. So let's enter the length and width of the thermal pad. Let's go with 0.393 inches. The thermal conductivity of copper is 9.78 watt inch per Kelvin, but you're free to change it if you wish to do so. Then let's enter thermal conductivity of filler, about 0.2 watt inch per Kelvin. If you're not too sure what to add there, we also have provided a thermal conductivities of filler materials list here, which shows the attributes of various filler materials. So here you can enter the via height 0.62. Let's enter plating thickness of 0.0037, drill diameter of 0.015 inches, and a wear to wear spacing of 0.031. So click on calculate here next to the number of thermal wears button and number of thermal wears, and you can see that there are 72 wears that can fit in this arrangement for the thermal pad that we have given, and the thermal resistance of the wears are also provided here. You can also do reverse calculation wherein you either enter the wear to wear spacing and the number of thermal wears, and you can calculate the drill diameter, or you enter the drill diameter and number of thermal wears to calculate the wear to wear spacing. Yeah. Uh, So even with the best design practices, manufacturing RF PCBs comes with unique challenges. Being a PCB manufacturer, we have witnessed these four fabrication challenges in RF PCBs. The first one being that as PTFE is UV transparent, it will not absorb the laser energy required for the ablation. Uh, Also, scaling becomes challenging as each material in the hybrid stack-up has different movement characteristics during the lamination process. Uh, we have also seen that sub-assembly integration increases complexity during multiple lamination cycles, and the material might shift slightly with each press. Achieving a solid bond during lamination can also be difficult as different materials have distinct melt or flow characteristics and respond differently to temperature fluctuations. Uh, so here's how our expertise and processes help overcome or tackle these fabrication challenges. So at Sierra Circuits, our engineers use carbide or diamond coated drill bits to ensure accurate drilling with tight tolerances. We also incorporate CO2 lasers and carefully adjust parameters like wavelength and pulse duration to enhance absorption on smooth PTFE surfaces. We also use exact software systems to predict scale values and adjust drill parameters. Our experts also conduct X-ray inspections to detect voids and weak spots. Uh, we also incorporate high quality metallization process for eliminating these voids and preventing whole wall detachment. To improve the adhesion in hybrid stack-ups, we prepare the substrate surface with plasma etching techniques. Beyond fabrication, assembly is also another critical stage. Soldering these RF components requires precision to avoid signal degradation and reliability issues. RF components such as balance, filters, RF shields, all these require precise soldering. And poor solder joints or excess solder might cause solder bridging and assembly errors. Uh, so what we do here at Sierra Circuits is we use a high precision reflow oven with controlled temperatures profiles to prevent the component damage, and apply the correct amount of solder paste using a stencil to prevent bridging or cold joints. We also run an X-ray inspection for fine pitch RF components such as QFNs and BGAs to ensure accurate soldering. To ensure a manufacturable design, following DFM rules is key. We have listed 7 DFM guidelines here for PCBs with antennas. The first guideline is to place your antennas away from metal components, ground planes, and other conductors to prevent detuning. Position these antennas at the board corners to minimize interference from other elements. Uh, Also avoid covering antenna traces with a solder mask because it can really alter the effective dielectric constant. Uh, Please ensure that the antenna trace width and the feed connection have the same width. For VR stitching, the pad size should be drill diameter plus 6 mils. Uh, Also verify if the material has the required copper foils that align with your design specification. And another important step is when you select a material, check the available material thicknesses with your manufacturer. Before launching your RF product, compliance with regulatory standards is also essential. There are several regulatory standards that you need to be aware of. First, let's talk about FCC Part 15C. This regulation governs unlicensed radio frequency emissions. Then next we have the IEEE 802.11, which defines specifications for Wi-Fi. For those working on controlled impedance circuits, IPC 2141A provides essential guidelines. ETSI EN 300-328 regulates wideband transmission systems, including data transmission equipment with a 2.4 gigahertz ISM band in Europe. Finally, CIS PR32. This sets limits on conducted and radiated emissions from multimedia devices. So we have cited a few blogs and our design guide over here for your reference. For further discussion or expert advice, feel free to reach out. We're always happy to help. We also have various design tools and resources that you can check out at our website. We also have a PCB forum called Sierra Connect. You can always just, post your question there and our expert will get back to you as soon as they can. We also offer end-to-end PCB manufacturing services. Here's what we bring to the table. You can also explore our design services if you need assistance with your PCB design. That brings us to the end of the presentation. Please feel free to ask questions you may have. So the question is, if we do not cover the antenna trace with solder mask, how do we protect the traces from the environment?
You can have a gold finish. You can have a inig finish. Okay. Or you can have, I think, or you can have tinning. But the inig or gold finish will be the best. And it will also be smooth so that there is no roughness on the surface also.
So in our case, Conti use OSP finished surface. In such a case, I guess we need to use solder mask on the antenna trace, correct?
See, if you use OSP finish has a life only for about 5-6 months. Okay. OSP finish is normally used to take care of the time between the PCB manufacturing and the assembly if it is quite a wide gap. All right. Its life is not very long. And that is the reason why OSP finish may serve the purpose in the beginning, but it will not serve the purpose for a long time. Okay. Yeah. All right. If one is bothered about the nickel content in the inig finish or something, then there is something called a soft gold finish also, okay, directly or something like that. I mean, there are some things, but generally the nickel content is very small and the antenna trace generally should not be very long on the PCB. That is one of the things that one has to take care when designing. Whatever is the IC which basically is feeding the antenna, that should be close to the antenna chip. Okay, so that we don't have a long antenna trace. All right.
We have another question. When would it be better to use strip line with 2 vias instead of microstrip for RF traces?
I mean, strip line with 2 vias, I would not recommend that. Normally the RF traces for the antenna chip should be on the same surface as the antenna chip. Okay. Yeah. Strip line, vias, etc. Vias impedance is not very easy to control, and that discontinuity at the, the frequency at which we are talking about may not be very good at that time. And we want to feed to the antenna as much power, or receive from the antenna as much power. Okay. So we don't want any problems in that. So that is what the, the antenna chip manufacturers also in their application notes, that is what the suggestion they also give. Okay. And so it is not a preferred practice. What is the next question? Do you have a database of
recommended predefined stack-ups based on the materials you typically use?
Yeah, we are creating a library on our website, on our stack-up design tool. And there is, the library is slowly getting built up. It may not be complete right now, but we hope to complete it in another 4 to 5 months completely. Okay. So in any way, if you need a stack-up, we have, you see, in order to create a library, we have kind of internalized some definite rules of construction. So if you need a stack up, please send that inquiry to us and we will basically design your stack and give you the proper stack up. Maybe it is there in our library, in our internal library, and we have not yet exposed that to the tool as yet, because during the process of creating more and more library and more stack up designs, we are storing them in our internal database, and then at an appropriate time we will put it onto the tool. Okay. All right.
Thank you very much, Vandana, for presenting. Thank you everyone for joining. I will send you the slides and recording this afternoon. Have a good day, everyone. Bye-bye.
Thank you. Bye-bye.